Yeah, welcome also from my side. I'm Markus. I'm working since 18 years at SAP and since 6 years in the integration of LLVM into our in-memory database. What will I be telling today? First, I will explain what are the special challenges of an in-memory database of that environment. I will explain you what we are doing with LLVM in our database, and the focus of my talk then will be to show how did we met these challenges, these in-memory challenges with LLVM, what did we do there. So first, what does it mean to work in an in-memory database? When you have everything in memory, then an absolute must is you have not to crash. Sure, crashing is bad for every application, but for an in-memory database, you not only use all work that has not been committed yet, you also have to restore your complete state from disk, which can take up to hours. So you really have to make sure that you stay alive, whatever happens. May it that there is some very large query which brings you at your memory limits, or there is some script kiddie which tries to look how deep he can nest his function calls to bring you to your borders, or also someone just building an endless loop. You have to find a way out of these situations. Further, sure, in a database, you need make heavy use of parallelization. Also the SQL semantics of arithmetics is slightly different than what you typically have. SQL has this special value of null, which really means undefined, not an arithmetic null, and which has to treat it explicitly. And since you do everything on the fly, not also the execution time, but also the compile time really matters. What are we doing with LLVM? We use LLVM as compiler backend, one for stored procedure, just for doing everything which you cannot express with normal SQL logic, where you need variables and such things. Yes, like other databases have this as well. And this is a rather new development. We also now try to use LLVM to execute classical SQL queries. So we have a query plan from the optimizer. Then we generate a program that executes this query plan and then compile this query plan using LLVM in order to get significantly faster execution. There is some years old a paper from Thomas Neumann on using LLVM for database query. And Thomas Neumann was also the guy who initiated within SAP the idea to do this query execution based on LLVM. And since there are several use cases, and to simplify the generation of the LLVM-IR, we put our own intermediate language on top of the LLVM-IR to simplify the generation there. This is a very small sample. You can see here just a very basic add operation. And you see the LLVM code we need is a little bit bigger. One point I mentioned there is, yes, we need to do overflow checks whenever since that is required by the SQL semantics. We also have to have some additional work, since we cannot use exceptions, since once we started with LLVM and Windows and exception handling between LLVM and Windows was not compatible. So we used the technical return value to indicate an error situation. And we also have an implicit parameter for passing some additional information, and also the information when an error occurred about the stack trace and these things. The rest, it's rather basic usage of LLVM interfaces. Yeah, that's about what we are creating there. A short look at our architecture, very rough overview. We have our users either creating these queries or stored procedures. There's some code generator producing the intermediate language. And then we use our compiler to generate the LLVM-IR. And then we are very happy that LLVM takes the job to create the actual binary. Since I already mentioned, we have different use cases here, queries, stored procedures. And we have to reflect this also in our architecture. And since we do not want to have specific compilers, we have made a separation in our software between the core compiler, which handles the language, and the type system, which knows the data types and methods which are specific to the use case. So yeah, we can serve different stakeholders basically with the same language, with the same basic architecture. We started using LLVM in 2010, and we were there rather fast to integrate. The first productive version was already available a half year later, so it was very fast to use the APIs there. We were very happy with the, we were very happy with the switch to the MC-JIT, since that brought us improvements in terms of multi-threading and concerning integration of debug info. And also since then, we have continuously upgraded to newer versions. Also, we also always have some delay until when we go to the latest versions of LLVM. I will explain later from where this, what causes this delay there. Yeah, overall, we are very happy that we have chosen LLVM. The quality is really excellent. We have not experienced functional regressions once we switch to a new version, and that is for software a really great thing. So yeah, thanks to the good tests you have in LLVM, that's really a great feature there. We also found the APIs easily to consume. It took us half a year, yes, to have the first productive version. So that went also really well. And we also like the supportability, both the traces you can have when you have problems in the compilation with LLVM itself. And also, it is really great to have the ability to integrate GDB or some other debugger if you have a problem with the code you have generated. So, as I said, the main focus is on how did we meet these challenges we have in the in-memory environment. And I put the focus on 3 of these. How to interrupt endless running procedures, how to deal with the out-of-memory situations, and what we did about the compile time problems we have. First, yeah, how to interrupt long-running or endless operations. The basic idea is rather simple. Besides the normal loop condition, we have an additional flag which contains a pointer to a memory location where the transaction abort flag is stored. And just whenever we have a loop condition, we check not only the loop condition, but we also check if the abort of the transaction has been reached. This is rather fast. It's about 0.3 to 0.5 nanoseconds per loop iteration. So for us, it does not really hurt. There is one drawback. Most optimizer passes don't like volatile reads, and for example, loop unrolling passes also just stop there, can't do anything there. Sure, they don't know how to deal with this volatile read. But overall, this is working rather fine. Yeah, the in-memory, the out-of-memory problem is much more complex for sure, but the basic principle is also known since years. It means you have to do exception-safe programming. You have basically everywhere in your program, you have to be ready that an exception may occur. And yeah, the main paradigm to handle this is this resource allocation is initialization. So whenever you have an allocation or another resource you acquire, you have to assign it to an owner, and this owner in his destructor has to take care of the deallocation. So you can either use a member of an object, or we have also unique pointers, shared pointers. So yeah, that's the main point. Really, consequently, when allocating something, put it to an owner who takes care during destruction. It definitely also helps if you, in your coding document, if you have members, pointers in your object, which one do you own and which not. That's just a simple comment when writing the source code, but really when later analyzing or when reviewing the code, it really helps to know, is this code intended to be owned by this object or not? And for sure, destructors are used for cleanup, for exception unwinding, so they must be no-throw. So you cannot create a free list or such things in a destructor. Sometimes such things happen, but that's definitely, you have to take care to only really do cleanup things in a destructor. Is it possible to test software for systematically for out-of-memory situations? And yes, it is. What basically, it's not that difficult, since C++ allows overloading of operator new, either globally or class-specific. So the main idea is just overload operator new and have some kind of counter who says, okay, I will fail at the nth memory allocation, and this value of n I can iterate. I can basically run my test in a loop and increase n as long as everything runs fine, and make sure in the meantime nothing has crashed when any of this memory allocation failed. Just I have to have somewhere catch it, to retry my test, and then somewhere it should go through, and in the meantime I'm able to test every location where an out of memory could occur. What can you find with this testing? A code similar like this we have found in an older LLVM version. Interesting question. We have here a destructor, and at the end of destructor, someone is setting a member variable to a specific value. The first thing we were wondering about, who can read this information? Any idea? Yeah. 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 Not exactly. Operator delete. If you have a class-specific operator delete, then that is exactly what happened. You have a class-specific operator delete, and operator delete was using this information. Yes, but it was there. Yeah. That's sure, yeah. That's we had also a very specific out-of-memory problem with it. Anyone an idea what this kind of communication between destructor and operator delete may cause, when this may cause trouble? Besides it's undefined. Yeah. Yes, that may be one. Yeah. Another issue, what we at this point had, what happens if the destructor is not called, and the destructor is not called if the constructor fails with an out-of-memory exception. So, yeah, besides it's undefined in general, when using operator new, operator delete, constructor, destructor, make sure everything is symmetric. Yeah, again, following this resource allocation is initialization principle. Just, yeah, whenever you allocate something, put it in someone's ownership who is guaranteed to take care of it. Okay, we indeed went through the complete LLVM. With the front end, we had about 50 patches or so, and then we were through. Also front end generation of LLVM-IR. So we were fine with this, whereas this about 50 patches are the reason why we always have some delay to come to a new LLVM version. With the backend, we soon found out that we won't make it through there. The point is, in the backend, there is much intermingling between objects, moving, function inlining, moving parts, statements from one function to the other. And in the meantime, you have a state where both objects think they own it or no object thinks owns it. So after some testing, some looking into this, we came to the conclusion we won't come through there, we won't be able to handle this. So there we decided for the backend operation to create our own process, use a separate process, create on the front-end side the LLVM intermediate representation, serialize it, send it to the separate process, optimize it there, generate the machine code there, send the executable code back, and then link it with everything in the database process we need there additionally for the runtime. With this setup, we have now been since 3-4 years quite happy there. And yeah, mainly we are at least able to survive with the out-of-memory situations. Okay, the second big issue, third big issue we are fighting with is compile time. If you have queries and you want to compile them on the fly, for the query execution, both matter, the preparation time and the execution time. So we really have to look at how large our compile times are. We had there two kinds of issues. One is dealing with large functions. Since we use code generator over several layers, generated code sometimes tends to become very large, especially very large within one function. And we have many nice optimizer passes in LLVM, which are used to speed up things. The problem is most optimizer passes have a nonlinear behavior. So if your function gets really huge, several thousand lines of codes, then you can end up with compile time of minutes or even hours. We made several tries, especially looking into the register allocator, trying to tell the register allocator to simplify its work or to say, here is some kind of point where you can safely make a split. We didn't succeed with this. So at the end, we decided to try to split up the functions our own automatically. Fortunately, we succeeded there with a rather simple heuristic, basically going sequentially through the program until we find a large enough block which can be split and which has also no problematic dependencies to the outside, like for example jumps or so. So here's a small synthetic example. Here you have a function just doing some sequential operations and having a variable declaration. And basically, when you split this into subfunctions, you turn the variable declaration into parameters to the subfunctions. Surely that will not cover every case of program you can think about, but for those stuff which is typically produced by the generator, this helps significantly. For example, it already helps significantly if you separate the loop body from the loop head, since then you eliminate a lot of phi nodes there, which create some work for register allocator and similar passes. The other side of is if you have small functions, very simple stuff. For example, you have a SQL query with a simple calculation, And then the classic approach is you fetch all the data, and then you apply on all data this numeric operation, typically using some expression evaluator, some kind of interpreter. And the new idea is now, you take you generate everything into one program. The program fetches the data, and also to be cache active, makes immediately the calculation and produces the result. And for sure, this is at runtime significantly faster than interpreting these things. But in order to really benefit from the compiled approach, you also have to amortize the compile cost. What costs do we currently see? In our intermediate language, we see about 1 millisecond compile time per line of code. That's about 200 microseconds per LLVM-IR instruction. And at the execution time, that looks much nicer. There we have about 1 nanosecond per line of code. And you can see our interpreter is much, much slower at execution time, but also uses less time at compilation. So currently our break-even point is at about 5,000 iterations. So either you have to have at least 5,000 data rows in order to amortize compilation cost, or you have to reuse the same query multiple times in order to amortize codes. So compilation of query is really a cool thing to speed up queries, but also, we are looking into ways how to improve the compile time to make it even more usable and usable in more cases. What have we been looking so far? For sure, you can reduce the opt level, especially since, as I explained before, some of the optimizer passes anyway are not useful for us. On the other hand, the less you optimize, the more code you have, and then the machine code generation tends to take longer. We have already started also to experiment with the fast instruction selector, but then we also had additional other passes which took longer. There we got today an idea, or yesterday ideas. We may be able to use function optimize attribute none or so to speed up the code generation passes. But there we would be still happy for ideas, what we can do if we basically say we have just the LLVM-IR and we would like to have a simple machine code from it, sacrificing some runtime performance for having a fast code generation on it. With this, I would like to open up for questions. Thank you very much for your attention. And by the way, if you are interested in compiler technology at SAP, you can contact me on this topic. Thank you very much.
Questions?
So I guess optimizing the query code sometimes isn't worthwhile because the query is not reused or might be too small.
Yes.
Is there a typical balance between long-running or often used queries where optimization really would benefit, or is 99% of the application scenario that you essentially want to get some code very fast? So is the emphasis more on compile time than at runtime of the query?
It depends. There are definitely long-running queries, queries which take 1 billion of data sets, or queries you will do often. The point is, you know it. Since you have the optimizer can tell you if you have to deal with 1 million or 1 billion or only 10,000 rows. So before starting compilation, you usually have a very good idea if you need full optimization. If this will be anyway long running and compile time doesn't matter, just get it as fast as possible executing. Or if you know, okay, that's only a few rows, so try to compile it as fast as possible in order to keep the overall time small. And we also, similar to the Java approach, we are also thinking about approaches where we say, okay, process the query chunk-wise, start the first 1,000 data rows with the interpreter, and then continue interpreting until the compiler is ready. So yeah, we have there some means to balance to vary the approach. But yes, that's typical in a database environment. Typically, you know how often you will use the code you produce, at least how often you will use it in this query.
Yeah, follow up. So is there also opportunity for optimization on the Llang level? So I could imagine like using program analysis to figure out whether values are null or non-null and so on could help to generate more efficient code later on.
We have so far done rather small optimizations there. We have a constant folding. We have done constant folding there, and temp stealing. These are the two main optimizations we have done there. If values may be null or not, that's typically not known at the point, also from the source code. The optimizer, that is something more likely the optimizer will know, or that the guy creating the code is more likely to know if he is working on data where no nulls occur. They are typically better able to know than the source code.
Thank you.
One thing I've been wondering is, are you doing side effects during query execution? Because, for example, for typical select queries, I would expect a signal handler that is jumping out to be much less work for terminating a query than it is to do those checks all over the place.
Typically, the query should be side effect free. Indeed, we discussed the idea to exit with a signal handler. The problem of the signal handler is then you have to somehow again arrange your stack, to come back. As once at some point, if you have a signal, you are in a signal handler, and the signal handler then somehow has to rearrange the stack that it looks again like you had a normal exception.
The question is, can you just do a 6-set jump, basically a long jump to the starting point where you started to execute the query, and just ignore everything that's on the stack?
Okay, the idea of a long jump, yes. The point is we have no side effects, but we have, for example, memory allocations on the way, or someone might have set a lock or such things. So so we guarantee our users that we do a regular stack unwinding, destructing everything that has been constructed, and thereby, yes, that's not an option.
As we had just had a 6-set jump idea, I'd recommend against that, because that's still relatively hacky in LLVM, because it's control flow you cannot see, and nobody has still fixed that yet. But using normal exception handlers might actually work, because you have lib unwind and unwinding information there. Maybe you can sneak something in there.
Yeah, so we have to rethink it. I think we can rethink it now. As when we started, it was not possible on Microsoft Windows, since it was incompatible. Now I think with the latest LLVM version, this should now be possible to have this also on Windows.
So you have Windows exception handling, and I don't know, if you do some effort, you should be able maybe to use lib unwind on Windows as well. I don't see why you couldn't if you
Yeah,
wanted to.
that's something we have to newly look into. Yes, that's definitely now a possibility which has not been there before. Thank you.
Another point to the exception problems. Yeah, it's, I think, relatively deliberate decision of LLVM developers to say have no exceptions and then just don't think about the problem anymore. Of course, in a Clang setting, it's not so bad. If you crash in an out-of-memory situation, nobody will complain about that in a long-running process. Yet you're doing the only thing you can do sensibly, putting that in a separate process. And that's maybe not the worst idea anyway, because there may always be bugs in a compiler. It's a complex piece of code. But there's apparently really a point to having a stable, minimal LLVM part that would be exception safe for those front-end parts. That's actually a good point here. Maybe there's something you can upstream or contribute, or that we define such a layer.
As we had already also such discussions. That's one of the problems we unfortunately have on our side is the colleagues who doing this out-of-memory testing frameworks have not agreed to publish that. So we have the problem to provide test cases if we provide patches. So at least some of the, not all, some of the patches are a little bit hacky for us, but some of them we definitely could provide. But yeah, then we have the problem, how do we provide the testing environment that someone can review it and say it's okay. So that's the point where we currently don't know how to proceed.
Yeah, hi. Previously, there was a SAP HANA database engine. Now there's also Vora, a newer engine. I was wondering, so how does code generation happen in HANA? How does it happen in Vora? What is the difference? How are they related?
The code generation in Vora happens using Clang. There was also some differences in the history. They started in an environment where they did not care that much about the out-of-memory situation. And since they also had not this stored procedure approach, for us, Clang was just too rich. Too much possibilities which we do not want to offer the normal developer. Therefore, we decided to go with a subset of what C offers. And for Vora, they only used it for query execution internally in the machine, and therefore they were happy to have the complete Clang available.
It sounds like it's totally disconnected teams, different product.
The teams are separate. They know of each other, and we share some information, but it's separate. Yeah, it's definitely separate development teams. Yes.
Okay, thanks.
Any more questions? In that case, thank you very much.
Yep.